I'm going to work some problems here that a student asked about, so I want to share those with everybody. This is from section 7-2, number 6, 7, and 10, and this is from the online work. And so my point in saying that is your version of the online work may be slightly different than this, but it's the general process. Okay, so 6 says, find the volume of the solid generated by revolving the region bounded by the graphs of the equations about the given line. So we have x equals 9 as the given line. So let me draw my little axis system. So we'll call this 9. I'm going to go around this line here. What do we have? We have y equals x, so y equals 0. Y equals 0 is just the x-axis. Y equals 8. So we call, I'll call this 8 here. And then x equals 9. Okay, so there's no gap between the shape and the axis of revolution. So it's going to come up here so far, then go across like that. And down here, and then right there. So it's going to revolve around this axis. So when we think about this, we will have our approximating rectangles perpendicular. This is 7.2. So the approximating rectangle is perpendicular to our axis of revolution because we're looking at this shape as it goes along that axis. Now this side over here is just going to be 9. And what's this side over here? I mean, this is x equals 9, and over here this is x equals y, so that the height, if you want to call it the height or width, but I'm going to call it height to stick with our notation, the height of this rectangle, h of y, is going to be 9 minus y. And our r of y will be 0. So our volume is going to be pi times the integral from 0 to 8 of 6 minus y squared dy. Sorry, not 6, 9. Minus y squared dy. So the volume is going to be pi times the integral from 0 to 8. That's 81 minus 18y plus y squared dy. So it's going to be pi times 81y minus 9y squared plus y cubed over 3. And it's going to go from 0 to 8. Sorry, using this new tablet is a little awkward. Okay. And this should be a squared. Okay. So we're going to have pi times 81 times 8 minus 9 times 8 squared plus 8 cubed over 3 minus, if I put 0 in, I just get 0 for those. So that's going to be what? Put in my handy dandy calculator. (81 times 8 minus 9 times 8 squared plus 8 cubed divided by 3 is what? Let me get put this in. Fraction or exact mode. answer is 7/28 over 3 times pi. That's the pi right there. There's our answer. I hope that makes sense. Next one, find the volume of the solid generated by revolving the region bounded by the graphs of the equations about the x-axis. And we have y equals 9 over the square root of x plus 1. Y equals 0. Now y equals 0 is the x-axis, x equals 0 is the y-axis, and then x equals 3. So we have a curve. Now if x was 0 for this y equals 9 over the square root of x plus 1, if x is 0, we have 9 over 0 plus 1 is 1, square root of 1 is 1, so it goes to 9. So I'm just going to call this 9 right here, and it'll curve down. Now if I put 3 in there, 3 plus 1 is 4, square root of 4 is 2, so 9 halves is as far as down as it's going to, for the sake of our graph, call this 3. Call this 9 halves, 4.5. Not drawn to scale, but I think you get the idea. And then we need to have it rotate about the x-axis, so it's going to go around the x-axis. So let's draw our approximating rectangle. So what's the height of that rectangle? H of x is going to be what? Well, this upper curve is 9 over the square root of x plus 1. And the r of x equals 0. I'm going to try a different pen here, see if it works any better. So our volume is going to be, it's like a pi r squared, so pi times the integral of 9 over the square root of x plus 1. I don't like the way that looks. Dx. Then limits of integration, we need that. Going from 0 to 3. Okay. Oh, forgot this has to be squared. So our volume is going to be pi times the integral from 0 to 3 of 81 over x plus 1 dx. That's going to be what? Well, the 81 can come out with a pi, so it's 81 pi times, and then we have basically 1 over x plus 1. You integrate 1 over x plus 1, you get a natural log. I'm having a lot of luck with this today. Back to what I had. Natural log of the absolute value of x plus 1 from 0 to 3. So we have 81 pi times the natural log of the absolute value of 3 plus 1 minus the natural log of the absolute value of 0 plus 1. So that's going to be 81 pi times natural log of 4 minus natural log of 1. So that's 81 pi times 2 natural log of 2. 4 is 2 squared. And the natural log of 1 is just 0. So we can call this 162 pi natural log of 2. Or call it 81 pi natural log of 4. They're the same thing. Hope that helps. Let's go on to the last one, which is number 10. Okay, this next problem says a manufacturer drills a hole through a center of a metal sphere of radius r. The hole has a radius r, little r. Find the volume of the resulting ring. I'd hesitate to call it a ring, but okay. So imagine that you have a sphere. Okay, and there's going to be this hole drilled through it. We want to know what the volume is, and it's not really enough just to find the volume of that cylinder and subtract it, because you have this end cap is gone and that end cap is gone, so not just the cylinder is gone. One way to visualize this problem is that of a semicircle, and it's rotated about the x-axis. Might as well center this here. And in this, we could, I want to change colors, make this maybe, come on. From yellow, let's go to maybe orange. So imagine this is that hole that's cut out, and it'll have radius with height r, little r. Okay. And then the radius of this big curve is capital R. So we want to come up with an equation that has this upper curve subtracting the lower curve. So let's think for a second about the equation of a circle. A circle is x squared plus y squared equals, I'm going to use the capital R because that's what we're using for the radius of this big, the sphere for this circle here, capital R squared. Then we solve for y. We'd have y squared equals capital R squared minus x squared, and then y would be plus or minus the square root of capital R squared minus x squared. And the point I want to make is, I mean, there's a plus or minus, so we have an issue that, you know, it's not going to be, if you drew the whole circle, it's not going to be one-to-one, so it's not going to be a function. However, all we're concerned about is the upper half, and that's what's going to rotate about the x-axis. So we will look at y equals the square root of r squared minus x squared. So just the positive part. So I'm going to take a lot of space in this one. So we have this bounded by that curve there, and then rotated. Now, this curve up here would be the square root of capital R squared minus x squared. And then down here, this is just going to be our R. What we want to know is the start and end points. It's not going to go from capital R to R. It's not going to go from out there, sorry, negative R to R, negative capital R to R, because it would have extended that far, but that drill has taken that portion out. So instead, it's going to go from this place here to this place here. So we want to set equal to each other these two equations. Where do they intersect? So in the case 1 is equal to y is equal to r, then y is little r. Y is equal to the square root of capital R squared minus x squared. So if we set little r equal to the square root of capital R squared minus x squared, squaring both sides, little r squared equals capital R squared minus x squared. And if I want to solve for x, we'd have negative capital R squared plus little r squared is negative x squared, because we want to see these x values. So then if we multiply by -1, then capital R squared minus little r squared equals x squared. So x would be equal to plus or minus the square root of capital R squared. That's a bad looking R. Capital R squared minus little r squared. And so over here we'll have ourselves the negative square root of capital R squared. Ugh, so bad. Square root of capital R squared minus little r squared. And over here we'll have positive square root of capital R squared minus little r squared. So that's this one here. So we really have pretty much everything we're going to need to set this thing up. It might be useful then also to look at our approximating rectangle. And on the high side we have the square root of r squared minus x squared. On the low side we have r. So as we set this up, our volume is going to be pi times, now integral, I'm going to write this real big just because we have so much to write, the square root of capital R squared minus little r squared over negative square root of capital R squared minus little r squared times the upper curve, the square root of capital R squared minus x squared minus, and then we're going to square that part, minus the lower curve, which is just r. We're going to square that as well, dx. And so I think the setup is by far the hardest part of this. Let's do this math now. So we have the integral negative square root of capital R squared minus little r squared, square root of capital R squared minus little r squared. And then you square the square root, so we're just going to have a capital R squared minus x squared and minus r squared dx. Integrating that's not so bad because r squared, capital R squared, is a relative constant compared to x squared, and little r squared is really considered a constant compared to x squared. So what we have is r squared x minus x cubed over 3. I forgot my pi, didn't I? Minus little r squared x. And this is going to go from negative square root of capital R squared minus little r squared to the square root of capital R squared minus little r squared. Okay, I'm going to go to the next page. So where's this going to take us? By the way, I think what I could have done earlier on, and I didn't think about doing this until now, we could have gone from 0, because this is symmetrical, from 0 to the square root of capital R squared minus little r squared, and then eliminate it and just call it 2 pi. But anyway. So now we're at pi times what? Capital R squared. It looks really bad, but let's bring this through, see what happens. Capital R squared times the square root of capital R squared minus little r squared minus 1/3 times the square root of capital R squared minus little r squared cubed, so that's going in place of the x, minus little r squared times the square root of capital R squared minus little r squared, and then minus capital R squared times negative square root of capital R squared minus little r squared, minus 1/3 times the square root of capital R negative of the square root of capital R squared minus little r squared cubed, and then minus little r squared times negative square root of capital R squared minus little r squared. Okay, and close that parenthesis and close the bracket. Okay, let's see what's going to happen now. Well, something I want to look at is, first of all, we have this capital R squared times the square root of R squared minus little r squared. So we have capital R squared times the square root of capital R squared minus little r squared. And then I have, if you look down further, the negative of that, so it makes it plus capital R squared times the square root of capital R squared minus little r squared. Then I have minus 1/3 of the square root of r squared minus little r squared, capital R squared minus little r squared, so that's going to be minus 1/3 times, and that's going to be r squared minus little r squared times the square root of r squared minus little r squared. That's because it's cubed, so you get one of them out of there. And if we look further down the road, we had minus the negative of the negative, so that gives me another negative 1/3. It's the same thing then. Capital R squared minus little r squared times the square root of capital R squared minus little r squared. And then we have this minus r squared times the square root of capital R squared minus little r squared, and then minus the negative of the negative makes it minus r squared times the square root of capital R squared minus little r squared. Okay. Okay, so let's keep going. We have pi times, so two of those, two of the r squareds, capital R squareds, 2 capital R squared times the square root of r squared minus little r squared, minus 2/3. Now watch this. This is 2/3 because you have 1/3 and 1/3. So 2/3 capital R squared times that radical, and minus the negative makes it plus 2/3 of little r squared times that radical, and then we have minus 2 times little r squared times the square root of capital R squared minus little r squared. Okay, so we're almost there to bring it all together. So I want to point out we have 2 minus 2/3. So what is 2 minus 2/3? That's 6/3 minus 2/3 is 4/3 r squared times the square root of capital R squared minus little r squared. And then we have 2/3 little r squared times the square root of capital R squared minus little r squared, minus 2 times little r squared times the square root of capital R squared minus little r squared. So the point is it's 2/3 minus 2. That's 2/3 minus 6/3 is minus 4/3 little r squared times the square root of capital R squared minus little r squared. Now from this we could factor out the 4/3 and that radical, so it becomes 4/3 pi times the square root of capital R squared minus little r squared times capital R squared minus little r squared. Or you could summarize it one more step. You have the radical times that, this is essentially the radical squared, 4/3 pi times capital R squared minus little r squared to the 3/2, because you have to the 1 half makes 3/2. And that's it.